So the Bohr model that we've been looking at, or the planetary model of the atom, where you have the nucleus in the center and you have the electrons going around the nucleus like planets going around the sun. Um, Bohr did all his calculations on the hydrogen atom, which only has one electron. And scientists found that when they took Bohr's ideas and they applied it to other elements, such as helium with two electrons and lithium with three electrons, etc., that the calculations didn't work out. And so what we learned from this is that the Bohr model is incorrect. So this is not how we see the atom today. The Bohr model is very helpful when you are looking at the energy levels that you find the electrons on. So you have a nucleus, and then the first energy level you have two electrons. That correlates with the first period on the periodic table, or the first row on the periodic table. And the second energy level has eight. And if you look on your periodic table, the second row of the periodic table has eight, etc. So we do use the Bohr model to describe those energy levels of where you would find the electron, but it is incorrect. So electrons do not go around the nucleus in an orbit. So scientists were kind of discouraged by figuring this out and with the Bohr model, and so they went back to the drawing board, and they went all the way back to looking at electrons as if they were a wave or a particle. And so this was the big debate. Einstein thought it was a particle. Other people thought electrons or light behave like a wave. But we are going to find that the answer to this question is yes, that electrons behave both as a wave or a particle. Let's look at how light behaves as a wave. So three ways we can show that light behaves as a wave. So number one, um, light acts like a rock thrown into a pond. It bends. So when you take a rock and throw it into a pond, you see that the energy of that rock falling into the lake, it ripples out. And we find the same thing with light. So when you are going camping and you have a flashlight, if you look at the flashlight, you'll notice that the light just doesn't come out in a beam that is the width of the light bulb. So it's not a 3-inch beam that comes out. Instead, it comes out and it spreads out. And so that's what we see with light. So in this first picture, we see a large slit, and as the light goes through, we can see that it bends around that slit or that opening. And in the second picture here, we see that the opening is a little bit narrower, and we can see the light bending even more. So this is showing that light behaves as a wave. What if we have two openings? So this is a double slit experiment. So you have two openings. You see that you have two openings and they will both bend, and you see where they start to overlap. And when they overlap, they can that can be two crests coming together, and so it will end up being doubly large. If you have two troughs coming together, then it will be doubly large the other direction. And if you have a trough and a crest come together, then they will cancel each other out. So recall that a crest is the top of a wave and a trough is the bottom part. So you end up having what's called an interference pattern. And so that is demonstrated here. So if this were to project against the screen, you would see that you have areas of high intensity and areas where they cancel each other out that would be dark. So this is called the interference pattern. All right, a third way that light behaves as a wave. This is a laser that is shown through a gradient, and you can see those waves. All right, but what about light behaving as a particle or a photon? So again, Einstein and Planck, they were behind this. So Einstein's photoelectric effect, which he received the Nobel Prize for, if if you have a photon that has enough energy and you fire it at a metal, you can liberate electrons from that metal. So it's called the photoelectric effect. And this is in some ways how solar panels work for solar power. So those photons come in and they hit a silicon material and it liberates electrons that are able to power whatever you have hooked up to your solar panels. All right, Louis de Broglie, he combined Einstein and Planck's equation. He basically said, you guys are talking about the same thing. So you're both talking about energy. If we put both your energies together, then we can put the right side of your equations equal to each other. We can replace the frequency here with the speed of light over the wavelength. And what de Broglie postulated is that everything that is moving has both a particle nature and a wave nature. So this was kind of a landmark a landmark idea that everything has both a wave and particle property as long as it's moving. So I was doing some calculations and I figured out that if you had a person just walking down the street, they would have a wavelength of that. So as you can see, it's really super, super, super small. And so and this is because Planck's constant is so small. So the larger the object is, the moving object is, then the less likely the wavelength is going to have any importance. And so a person walking down the street, you're not going to notice a wavelength. It's just too small, okay? But with electrons, because they are so small, now the wave nature of the electron is important because it is so tiny. I do have an animation that you can watch that is with this video that you can look and see how electrons behave both as waves and as particles. Now, a curious thing about things behaving as waves or particles, and they're able to have both of these, is that you can't prove their wave nature or the particle nature at the same time. And so this is called wave-particle duality. So again, every moving object or particle has both wave and particle natures. Again, the smaller the thing is, then the less likely the wave nature is going to be important.